de Broglie wavelength. So this won Mr. de Broglie a Nobel Prize. And you'll be surprised, what did he do to earn this one here? So this is momentum for a photon. This is equal to energy divided by c. And this is from E squared, it's equal to c squared p squared plus m squared c fourths. So this is the energy equation for relativistic. So relativistic particles, meaning the particle that move at speed that's close to speed of light. So relativistic particle means a particle that move at the close to speed of light. So for photon, this is zero. This is zero. So then you have this relationship, and that's how you find out the momentum for photon. And we can apply the Planck's constants. So the energy is defined as h times frequency of the photon. And the c, according to the wave equation, this is equal to frequency times lambda. So you can see they cancel out. So this is equal to h divided by lambda. So what de Broglie did, it seems very, very simple. So what he say is that, well, what happened to electron? And all matters. Meaning like a, for example, like a baseball. Does it have wavelengths too? Right, so then here, this one here says lambda for the photon is equal to h divided by p, right? So this is the lambda equation. So de Broglie was very brave. He said, well, it should be that electron has a lambda too. Electron, even though it may look like it's moved like this, electron actually is moving like that. And there's a lambda for that. And he was right. So once he put that in there, so h, so for electron, for example, let's say electron is moving at velocity equal to 10 to the 4 meter per second. And we know the mass for electron is equal to 9.1 times 10 to the negative 31 kilogram, everything in SI units. So then this is, we're just gonna put P, right? Put P using momentum, which is mv for electron. So me, right? So mev, so mev. And the v here is 10 to the 4. And if we go and calculate this, so this is 6.6 times 10 to the negative 34 joule second. And this is 9.1 times negative 31 kilogram. And then times 10 to the 4. And this will come out to be about 73 nanometer. So this is close to photons lambda. So this is in a UV range, ultraviolet. So you can do the similar things, and instead of for electron, you can do it for mass of proton, for example, and the velocity, right? So you can do the same thing, and then you can calculate that too for the proton. And you can also do that for, say, just an object with a mass equal to say 0. Just say equal to 1 kilogram, and the velocity equal to 1 meter per second. Right, so we go. Okay, then this lambda for this ball that's traveling at this speed will have the wavelengths, de Broglie wavelength, equal to 6.6 times 10 to the negative 34, and then you have 1 here, so it's just that. So that's your wavelength in meter. So that's very, 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 very small, right, compared to the wavelengths. And proton would have wavelengths that's smaller than this one here, right? It could be, looks like it's about 1,000 times, so it will be, you know, this times 10 to the negative 3, right? So this could be like something like a 73 times 10 to the negative 3 nanometer, right? So that means it's in picometer, right? So you can see for a ball, you know, an object, it's very small, negative 34 meter. So, all right, next we're going to talk about the hydrogen model. So it's energy level diagram. For hydrogen. So we're going to introduce like 3 series. One is called Lehman. So this one is from the excited state. So the excited state can be 2, 3, 4, and so on and so forth, and jump back into the ground state. And since ground state has less energy, and this one has a higher energy, so when you jump down to a low energy state, you would emit an photon when the electron jump down from the excited state to the ground state. And the photon will have the energy of the differences of the two, right? So if they say, for example, it's 2 to 1, then you would then calculate the minus 13.6 EV, and then divided by n squared, so that's 1 square, right? minus 13.6, and then divided by 2 squared, right? And that will be the energy for the photon that will be emitted. So this looks like negative, so you need to reverse it, right? The energy for the photon will be the minus of that. So second one is called Bowman Series, right? So this is the name for series. The series is for the, because you can jump from 2 to 1, so this is 1. You can jump from 3 to 1, from 4 to 1, so it's a series. So this is called the Bowman series. So then this one here will be jumping from excited state starting from 3, 4, 5, and so on and so forth, to excited state 1. Okay, so that would be, oh sorry, this one actually is called state 1, and so this one here will be jumping to the state 2, right? There's the ground state 1, and this will be excited state 2, right? So similarly to this, I'm not going to show that. And number 3, it's called Paschen, P-A-S-C-H-E-N, Paschen series, okay? And this will be from 4, excited state 5, 6, and then back down to the state 3. And so you will release photons, of the energy differences between the states. Okay, we're going to stop there. Thanks for watching, and we'll see you in the next one. If you enjoy it, please subscribe and share. Thank you. Bye-bye.